All right, so can we? Shall we? So in question 6.3, look at the right hand side view of this wheel or roller or pulley, whatever you want to call it, and see if there are any mistakes on the right hand side. Are there or are there not? Yes? What is missing? What is there that should not be there, and what is missing? You mean this one? That's missing? Okay. What else? Another one. You mean these two guys? They should be there or they should not be there? They should not be there. They should not be there. Okay? Better? And of course, these vertical lines, they would correspond to this arc of the rim. Yeah? So these are little or subtle mistakes that are very easy to be missed out, and unless until you have an eye for the drawing, it becomes a little difficult for you to catch these mistakes. Okay? So the more the practice, the better for you. I'm sorry I'm making you work a lot, but bear with me. So quite a few of you guys would have, rather they asked me what FADC means. You know, when I was working on these drawings, I did remember, I think, what FADC meant, but I don't remember it now, so I apologize for that. You know, I have been asking God since yesterday, and I have invested about 2 or 3 hours, and God gave me a lot of answers, one of them being flight automated digital control, and that had absolutely no relation to engineering drawing. But I'll tell you what, so don't worry about FADC for now. If I get an answer, I'll definitely share it with you. But what I can tell you is when I was working these drawings, I took this depth as half of 5, that is 2.5. Okay, so as far as you guys are concerned, as far as your labs are concerned, just take that dimension as half of 5. Okay, other than that, don't worry about it. All right. This problem, problem 6.2, which is an optional problem in your lab. Quite a few of you guys came to me and said that if you take the revolved section, the section actually covers pretty much the entire thing. Okay, maybe it spills out. All right. So one option that you can think about is maybe take this dimension as 170 instead of 130. For those who have already solved this problem on Monday and Tuesday, don't worry about that. For those who are going to be working tomorrow and day after, take this dimension as 170 and see if you get a proper revolved cross section. Okay? An alternative, of course, is to show this revolved section in this view, because you already have this dimension. You already have this dimension. All you need to do is get this dimension, revolve it, spin it, and show the corresponding revolved section that you would show here over there. That is a possibility. Okay? Any questions so far? Any questions? Yeah? These lines? You mean these lines? Yeah, so they shouldn't be there because this slanted part is essentially tangent to these cylindrical surfaces. Is that what your question was? Yeah, so they shouldn't be there. Okay, All right. Yeah. Yeah. It would be a T, no? No. So this is a slightly different figure here. This figure is not the same as this figure. For this case, the cross section would be a T. But what I'm trying to show, or what I'm trying to say via this figure is that there is a possibility that you can show the revolved section in this view as well. Okay? Yeah?
If we take a sectional view of the body and we consider the middle joining part to be a supporting element, then what we have that, what we say that the supporting element going all the way to the center of the spindle.
So I'll tell you what. So I'll talk about sectional views a little more today. Okay. So see if I'm able to address your question. If not, then we'll talk about that after class. All right. So fasten your seat belts. Another mistake. Wonderful.
In the same rod, there shouldn't be another line which are actually the cylindrical.
What? Yeah? Yeah? Yeah. So it would not be, well, yeah, so these lines won't be there probably. So this line and this line, they will probably not be there because it's nicely blend with that thingy. Okay. Nice eye or nice pair of eyes. You know, my wife is an ophthalmologist. So she's an eye doctor. Anyhow. Okay, so today's lecture is going to be a little long. I want you guys to fasten your seat belts. So today will be quite a bit of reading. So I have been giving you so much of assignments and so many problems to solve that I don't think it's fair on my part to expect you to ask God or read your Bible. So if you have not found time to ask God about your questions or read your Bible, don't worry, I'll help you out. I did that on your behalf. So with regard to sectional views, what does God or Google say about these views? So I did a little bit of reading myself. I asked God, and I got quite a few answers. I want you guys to follow me because I'm going to be reading all the text slowly, gradually. Okay? And the important text is something that I have highlighted or colored using a color different than black. Okay? In section view drawings, hidden lines. So this is from University of Texas at Austin. In section view drawings, hidden line representation is omitted in that part of the view with the section lining. This is important. A correct conventional representation of the full section in the front view omits these hidden lines, something that you know. In all cases, the top view of the drawing is a standard orthographic view complete with visible and hidden lines. Okay? So front views, section view, top view is the entire complete view with all visible and hidden lines. Okay? Something that we know. Visible object lines, this is about precedence of lines over each other. Visible object lines take precedence over hidden and center lines. Hidden lines take precedence over center lines. Cutting plane lines take precedence over center lines when locating the cutting plane for the section view. Center lines are included in the section view, but hidden lines are omitted. Okay? Something that we know. Some more. Certain features of engineering parts are generally not sectioned even though the cutting plane may pass through them. When the cutting plane passes through the length of supporting ribs, lugs and other thin parts, the feature is represented without section lines to avoid a misimpression of solidity. So this is a new phrase. Misimpression of solidity. I'll talk about that. Well, what it says is if you have a feature and if you have a section plane that is parallel to the feature, for example, this is a rib, and if you have a section plane which goes or which runs parallel to the rib, then this guy is not sectioned. That's by convention. Okay? And the reason is to avoid misimpression of solidity. Talk about that later. In addition to thin structural features, parts not sectioned also include standard mechanical elements such as shafts, bolts, screws, nuts, rivets, keys, pins, bearings, and gear teeth. The shaft, bolts, and nuts of the assembly are not sectioned, even though they are cut by the cutting plane. Okay? Look at this figure, for instance. Okay? So you have a little web over here, or rib, whatever you want to call it. Okay? You take another view of this, section it. Okay? Look at this part. So the section plane is running parallel to the web. Okay? This rib is not sectioned. Okay? If you section it, you would see a picture like this. You would see a picture like this, and that would give you the wrong impression that this rib is actually, this web is actually quite thick and runs from here to here. Okay? It would give you the impression, this picture would give you the impression that material is present here and here as well. Okay? To avoid that misimpression, we do not section webs or ribs. Okay? But on the other hand, if your section plane runs perpendicular to these thin features, they get sectioned. Okay? Parallel, not sectioned. Perpendicular, sectioned. This is what I told, that the figure over there gives the impression that the entire object is solid. The web is not a thin feature. But on the other hand, it's okay to hatch this guy over here because the cutting plane is perpendicular to the rib or the web. Some more. When both the web and ribs are present in section views of cylindrical parts, for example, in this roller, you have got only the web but not spokes or ribs. But in this case, you have got both the web as well as spokes. Okay? When both a web and ribs are present in section views of cylindrical parts, the alternating sectioning rule applies, something that I have not talked about. When ribs are present in addition to the web, the usual convention for the ribs would result in a view identical to case A. If you section this guy, okay, you would see this part cross-hatched. Okay? Not this part. Okay? So this is a case with only a web that connects the hub, the center part of the roller, to the rim, the outer part of the roller. Okay? But on the other hand, if you also have these ribs, okay, what do we do? Even if the section plane is passing through these ribs, or even if the section plane is parallel to these ribs, we have to section it, because if you don't section it, if you don't section this guy and this guy, this section view would be identical to this section view. That would give you the impression that you have only a web and not ribs or spokes in there. Okay? All right. When ribs are present in addition to the web, the usual convention for ribs would result in a view identical to case A, which is what means to eliminate this misrepresentation. In this technique, only alternating section lines are shown in the cross-hatching style. So these guys, they are also sectioned. All right. So even if the section plane is parallel to the ribs, in this case, to avoid the misrepresentation between these two cases, the ribs are sectioned. Okay. So this is from other source, Kent State University. I'll go a little fast. Ribs in section not drawn if parallel to plane because tends to imply greater mass than actual. Drawn if rib runs perpendicular to the plane, and same is true for spokes. Conventional practice, sectioning is not a physical cut. This is something that I liked. Okay? So sectioning is not actually a physical cut, but it is a graphic cut. Okay? So, the physical cut and the graphic cut could be different from each other. They could be identical or different. Could be different, such as ribs not sectioned and spokes not sectioned. Also, items usually not sectioned are ribs, spokes, bolts, pins, and keys. Okay?
How does it make a difference and what does it tell?
Which one?
It's in section. Drawn and perpendicular to the plane. There is a section when the plane is perpendicular to it.
Yeah.
How does it make a difference?
Well, you then get the true thickness of the rib. No? You then tend to get the true thickness of the rib. Over here, you would not get the true thickness of the rib, but over here you will. So, that misimpression of solidity won't be there.
So now, in this case, we don't have, we know what the rib looks like.
Well, that's what the convention is. Yeah. Okay. So, keep this in mind. Sectioning is not a physical cut, but a graphic cut. Okay. Another source, conventional practices have been established to handle section views, which is what I was talking about. Conventional practices have been established to handle section views of special situations such as the alignment of holes, ribs, and spokes. They have described these conventions in 4 parts. 8.4.1, ribs, webs, spokes, lugs, and other thin features are not section lined when the cutting plane passes parallel to the feature. Again, something very similar. A rib or web is a thin, flat piece that acts as a support, something that I have been talking about for quite some time, supporting elements. 8.4.2 or rather 8.42, adding section lines to these features would give the false impression that the part is thicker than it really is. Okay? Something that I have covered, don't worry about it. What would the Bible say? Okay, this is what God said. What would the Bible say? Okay, so if you look at page 161, section 5, parts not section. Many parts, bolts, pins, shafts recognized easily by their exterior views than by sections. Okay, so it's better to recognize these guys by their exterior views than by sections. They may lie in the path of the sectioning plane. Such paths should be left in full view and not sectioned. Otherwise, the drawing will be difficult and confusing to read. 6a, spokes not sectioned. Even though the section plane passes through 2 spokes, sectional view must be made without cross hatching the spokes. Okay, something very similar. So, this guy actually differentiates between a web and a spoke. If you section these spokes, okay, these 2 figures, they will essentially be identical, and you will get an impression that this entire thing is actually a web, which is not true. Okay, so to differentiate between these 2 cases, where you have a web and where you have only these 4 spokes, these 4 spokes, rather these spokes, they are not sectioned, while or whereas the wheel is sectioned. The web is sectioned. Okay. Page 162, 6a, spokes not sectioned, Other machine elements treated in this manner are teeth of gears and sprockets, vanes and supporting ribs of cylindrical parts, equally spaced lugs, and similar parts. 6b, ribs in section. When the cutting plane passes longitudinally or parallel through the center of a rib or a web, cross hatching of ribs is not performed as if the cutting plane were just in front of them. Okay? So, even though the cutting plane passes through a rib, hatching is not done because we treat the cutting plane to be in front or behind. Ribs cross hatched gives a misleading effect, suggesting a cone shape implies presence of a lot of material. Okay? When the cutting plane cuts a rib transversely, right angle to its length or axis direction, it is always cross hatched. Lugs in section, a lug, which is very similar to a projected ear or projecting ear, that is what the Bible calls, of usually a rectangular cross section, is not cross hatched. If you look at figure 30 and the title of that, so small lugs, they are not hashed, they are treated as spokes or ribs. Large lugs, they are hashed, they are treated as the solid base of the part. Okay? and pages 161 to 165, if you get time, they are nice read. Okay, so if you guys are dozing off, wake up. All right, have some water. We'll take a little break, and if you have any questions, feel free to ask, and then we'll start with oblique views. So far, so good with regard to sectional views. Yeah? So these are the conventions that you would need to keep in mind. Okay, back to pictures, enough text. So we'll talk about oblique views today. You know, when I was a kid, I was a naughty guy, never was interested in studying. I always used to pick my bat and step out to play. My father had a hard time. So when I was maybe in the 3rd grade, 4th grade, 5th grade, as I said, I didn't study at all. My father used to wake me up at 1:30 in the morning or 2 in the morning, and he would make me go through the answers, make me read, and of course, he was also reading. And the exam was around 7 o'clock, 8 o'clock, 9 o'clock the next day, or the very same day. He used to wake me up with 2 cups of tea, and that's how I'm a tea person. But nevertheless, whenever he used to draw a cube, he would always draw the cube this way. And I learned to draw it this way. And when I did my TA 101 equivalent, when I was your age, first year, I came across the isometric view of the cube, and I wondered why was it that my father drew the cube this way and not the actual isometric view. So that perplexed me until I read about oblique views. I'll share what I read. You know, the 3 faces of a cube in orthographic views, they are shown like this. Okay? Front, top, left, right, orthographic. In the isometric, you have seen the cube looks like this. Okay? And if you think about it, oblique view is a nice blend of orthographic views and isometric views. Okay? So just imagine that faces which are parallel to the view plane, they get transferred directly in the oblique view. Okay? Faces which are parallel to the screen or which are parallel to the view plane, they get transferred directly over there, and you get to see the depth impression through the isometric views. Okay? So it's a nice blend of both these. Of course, when I say it's a nice blend, I get to see true features in a single view, and I also get to see the sense of depth in this. Okay? So once again, oblique views are a nice blend of orthographic and isometric views. But if you think about it, the projections or the projectors are parallel in all the 3 cases. Okay, you have seen that in orthographic views. How about isometric? Are they parallel or not? They are? They are? Okay. So in isometric, you know that you rotate an object twice to capture it on the plane of screen. Okay. So once again, if you have this object, you rotate it this way, you rotate it this way, okay, and this is your screen, and your projectors are coming straight out, perpendicular, all parallel to each other, but perpendicular to the screen. Okay. So the projectors are still parallel, right? They're all perpendicular to the screen. Okay. Orthographic, parallel projectors are perpendicular to the plane which is parallel to one of the principal planes of the object. Okay. So this is the view that you would see in case of orthographic projections. In case of oblique projections, things are slightly different. Okay. What is the difference? The only difference is the projectors are parallel, but they are not perpendicular to your view plane. Once again, they are parallel to each other. Okay. They go parallel to each other, but instead of being perpendicular, they go oblique and hit the plane of view. Okay. There is an angle involved which is now 90 degrees, like so. Okay. So, if you take the projections for the first face which is closer to you, you get to see a face like that. Okay. Once again, these projectors are not perpendicular to this plane, they are oblique, and that is the reason why it is called oblique projection. If you take the same projectors parallel to the previous ones, you get to see this face which is slightly offset to the previous face, okay, and that actually gives you the sense of depth. These are your edges along the depth direction. Okay. Okay. Once again, you would see certain edges, you would not see certain edges, just like in case of isometric views. So, edges that you see, you draw; edges that you do not see, let go. Okay. What is the advantage? What is the advantage? So, if you compare oblique views with isometric views, what is the advantage? I can see one. You do not have to draw ellipses. If there are many of them, you do not have to draw ellipses. Yeah? So, the true features will remain true features in oblique projections. There is a trick to avoid that. I will talk about that. Huh? If there is a circle here and there is a circle there, Google help you, God help you. So, you choose your frontal plane in such a way that you have many features which are, so to speak, circular, okay, so that you are able to avoid those features along the depth direction. Okay. So, the first advantage that I see is you do not have to draw ellipses, you can deal with circles, and that should be okay. And the second advantage is that it would still, the impression that you get by looking at these views, you would still get the three-dimensional impression somehow. Okay. So, this is where your question comes. You have to choose the frontal plane in such a way that you get to capture as many circles as possible, as many arcs as possible, as many complex features as possible. Okay? Because drawing ellipses along the depth direction would be quite difficult. Okay? So, this is your frontal plane. This is your depth direction. The direction of depth could be 30 degrees, 45 degrees, 60 degrees as specified. Okay. Best to choose 30 to 60 range. Okay. And you got two options. Option 1 is to retain the dimension along the depth direction, and if you do that, we call that oblique view the Cavalier view. And if you foreshorten the depth dimension to half, okay, the view is called the cabinet view. Cavalier oblique view, cabinet oblique view. Okay. In the first one, this dimension remains the same as the third dimension of the object. In the second case, this dimension reduces to half of the actual depth dimension of the object. Okay. I think it is possibly one of the simplest amongst the three schemes of drawing, okay, but I could be wrong. So, let us look at the first example. maybe it will be a nice idea for you guys to work it out on your sketchbooks if you have them. If your eyes are heavier, maybe that will wake you up. All right, so you got this object in front of you. Two views of the object is shown. Which one would you choose as the frontal view to draw the object with? Great. You guys are wide awake. So I'll draw Cavalier. Okay. What should be the dimension along the depth direction? Same, which is what? Look at the figure. 100. Good. So this is the bounding box that would encompass this face of the object. Okay. I choose this angle as, I think, 30 degrees. Okay, the depth direction. What is the length of these guys? What are the lengths of these guys? 100. And behind, I draw another bounding box. Okay, so your object is going to be what? Huh? It's going to be jailed within this box. It's going to be encompassed within this box. Okay? What would this plane correspond to? So this plane corresponds to this guy here. This plane is this plane. Okay? All right. So the first thing I would do is I would draw a bunch of circles. Okay. I see 3 circles. I'll draw 3 of them. Okay. This fine? Is this fine? All right. Now this is the plane that I draw behind this. Okay, looks like there's this contour bore here. Okay, so I'm going to be drawing this circle here. Okay, behind, which is pretty much like this. Okay. I'm drawing another circle on which plane? This plane. Okay, and this circle corresponds to this guy over here. Okay. I have drawn this arc on this plane. Likewise, I have drawn this arc on this plane. What am I doing? Okay, I've drawn this circle here now on this plane. I've drawn this circle here. The bigger circle behind the plane, on the behind plane, center lines, the arc over here, the corresponding arc at the extreme rear plane, so this is like a cylindrical feature. I'm drawing the ribs now. Okay, I'm drawing these 4 ribs now. And I start drawing the drawing. Okay. Once again, the process is very similar to the way you would draw an isometric drawing. Okay. Get to see these circles. You see a contour bore, so the inside circle. You start drawing the ribs, solid lines, second rib, the third one. You essentially draw whatever you see. See this arc. Okay. See that part of the circle on the left. You see the entire right circle. See that arc. You see the arc behind. Okay. See the arc on the left. You see the arc on the right. Draw a tangent line. And in a sense, finish this drawing. Yeah? There would be one more circle. Yeah, looks like. Where would that be? Over here? Yeah, there would be one more. Okay? All of you with me? Yeah? It's okay. The length of the rib. This guy here? Here? Over here? So the mirror of this rib on the other side. What are you talking about? You mean this guy? You mean this guy? This rib here, the other one here, this one, it does what? I can't hear if you. This rib ends 8 units over here, you mean? Okay, this one. Okay, I understand. I understand. So this guy would be a little short. This guy would be a little short. All right. I am permitted to make mistakes. But this actually gives you the essence of oblique view, right? So go back to your hostel rooms and draw the correct version of this drawing. Okay. Another one. All right, so this time I won't say a word. Okay. My presenter is going to be doing the thing. All you need to do is like concur or disagree. Okay. You have seen this object before. I'm going to be drawing the cabinet view, and the depth direction is going to be half of what is shown. Okay. It's going to be half of what is shown. Stay with me. Which view should I choose as the frontal view? Good. Bounding box for the circle on the left. Well, I was not supposed to say a word. All right, here you go. Shall we? don't worry about what I'm doing on the right, something that I just needed to figure out the depth of this part, okay? But you can follow this thing up in your slides. I didn't want to do any trigonometry, so I just wanted to solve it graphically. Don't worry about that. Okay, so once I do this little exercise, I figure the depth. Am I done? Okay. Okay, thank you. Thank you. Why are both the circles not in the same line? Centers of this guy and this guy? Are you asking why are they not on the same plane? Look at the figure on the right. Got it? So the cylinder on the right is pushed slightly backwards. Okay, so one very nice thing about oblique views is that it gives a reader the sense of the correct dimensions, okay, and also the sense of depth. Yeah? Which one? Yeah? Yeah? Basically the bottom view. So I'm looking at this object from the other side. Because if I don't draw that rib, then I'm missing something. Well, my intent, what is my, okay, all right. You know, I'm so glad you guys are participating, but just give me a second, give us a second. A moment of silence, please. A moment of silence, please. Thank you. Yeah? Well, what is my intent? My intent is to show the object as clearly as possible. Okay? So I got two goals here. Number one, to be able to show the true features as well as pretty much all the details of the object. Okay? And also to render the object some sense of 3 dimensions. Okay? So my goals are threefold. So I capture the true dimensions on the plane which is parallel to the screen. Okay? Along this dimension I capture the depth, and I choose the orientation in such a way of the object that I get to show all the details of the object. How does it matter? Does it matter? No, the object remains the same. I've just flipped it. I've just flipped it around. Haven't I? Well, you got two questions. You're raising two hands. Two questions? Any more questions? Eyes heavy? Shouldn't this circle be completed? Shouldn't this circle be completed? Is that what the question is? Well, it is. So part of this cylinder is hidden behind this surface. So you got to be very careful. So something very similar to the isometric drawings when you draw. I mean, you got to be very careful what you see and what you don't see. Yeah. Which rib? The dimension. Okay. The question is, why are we having the depth half? In isometric view, what happens? This is something very important. You need to hear me out, and you need to hear. Well, what happens in isometric view? The length becomes foreshortened, right? So to give that sense of foreshortening in the depth direction. Yeah, but you know, something that I will actually share with you is something really interesting. Nature. Okay? You guys know numbers, 1, 2, I don't know till when. Syllables, language, you guys know that. Okay? How about nature? Does it know numbers? You think it knows numbers? You think it knows the rules of mathematics that we have learned since our first grade, second grade, third grade? How does nature work? Laws of motion. Okay, that is our understanding of what nature, what we think nature, how nature functions, right? Okay, but nature, I mean, it doesn't function with numbers or language, in my opinion. I could be wrong, but in my opinion, the way I see it, you see a bird flying, you see yourself walking, you don't apply equations of dynamics, you don't apply fluid mechanics when the bird is flying. You do? Or nature doesn't do that, at least. Okay, so mathematics, it's good so long as you are able to understand something. It's great, but you don't have to apply mathematics everywhere. Okay, so just relax. Okay, take it as a nice blend of art and analysis. Yeah.
Sir, are we allowed to transition through the figure at some point inside the figure? So because in this case, if you want to show that rib is inclined, I think we should establish it properly in the main rib. If we want to show that it is inclined, we should establish it near both the ribs.
So what's your question? Are you allowed inside the rib?
Yes, inside the drawing.
Inside the drawing. Well, you can always use an arrowhead like this, an arrow like this, an arrow like this, possibly, and dimension outside. You can do that. If you want to dimension inside, I mean, nobody is stopping you from dimensioning inside. It's just to make sure that your figure is very clear and it is not interfering with the dimensions that you choose to dimension outside the figure. But if you have to dimension inside the figure, you are permitted to do so. Any other question?